slideshow and start from current. So as I mentioned before, I did make the mistake of saying two-dimensional motion, but we were really working with one-dimensional motion, since one dimension is just me going back and forth. Two dimension, as I showed earlier, was if I was going along a sheet of paper. All right, so last time we were talking about, we're considering the motion of a soccer ball. Let's say I was going left and or right. That was modeled by this function, where S was our position function, V is our velocity function, and then soon to be A is our acceleration function. And we did part A already. We determined and graphed the velocity function. And then we were, based off of that, we could tell when it's moving left or right, or when it was temporarily stationary. Stationary meaning when was it not moving at all. All right, so let's go on to part B. So this was part A. Let me move through those. Again, this was the movement of our soccer ball moving right, takes a pause, and then moves left, and then continues to move left further. So let's look at part B. I put up the important information, the position function up on top. Part B says determine the velocity and acceleration of the ball after 1 second, or at t is equal to 1. And let me go back one slide real quick. I'll come back to this. I just need to double check something. I just need to make sure what is our units, feet, and seconds. Yeah. There we go. So first, I'll give y'all some time to copy this down before I continue. Lots of word problems for this section because we're in the application chapter. So we actually already found the velocity function last time, but we can find it again just because we're starting a new day. How do I get the velocity function based off the given information up here? How do I find velocity? Yeah, we know velocity is the derivative of position. That was ds dt. So we had our position. So velocity, we know that it's the derivative of that function. And last time we said the derivative of that function using power rule was 14 minus 4t. This is my velocity function. But for part B, that's not what I'm looking for. I'm looking for the velocity at 1 second. So how do I find the velocity at t equals 1 second? Yeah, we're plugging the 1 into the function. Again, this is the velocity function. It tells me at any given t value, what is the velocity of the ball. So if I want the velocity at 1 second, I'm saying what's v of 1? Well, v of 1, that's saying replace that t with a 1. So I got 14 minus 4 times 1. 4 times 1, I get 4. And then 14 minus 4, I get 10. So my velocity after 1 second is 10. However, what is the unit of measurement for the velocity function? Remember, my position was measured in feet, and then my time was measured in seconds from earlier. So what is my velocity measurement? Yeah, feet per second. And we know this because, well, first off, my position, my velocity is how is my position changing over time? Position is measured in feet, time is measured in seconds. So I have feet per second. All right, so again, my velocity after 1 second is 10 feet per second. So this soccer ball I had is actually moving at a pretty fast rate. So velocity portion at 1 second, done. Now I want the acceleration at 1 second. Well, if I want the acceleration at 1 second, first I need the acceleration function. How do I get the acceleration function a of t? So the derivative of velocity, so dv dt. Derivative of velocity in respect to time. So I just need a derivative of velocity. Here's my velocity function. What is the derivative of this function? So this part is 0. What's the derivative of this part? Yeah, so we have, in particular, -4. So I have my acceleration function. But again, I don't want my acceleration function. I want the acceleration after 1 second. So just like before, at v of t, v of 1, I got a of t. Now I want a of 1. What's a of 1? Is there really even anything for me to plug in for? Yeah, so first off, we have -4, because there's nothing to plug in. There's not even a t to replace for right there. This tells me, yeah, my acceleration at 1 second is -4. Now I gotta figure out what is the unit of measurement for acceleration. Yeah, so to get this, what was velocity measured in again? Feet per second, right? What is time measured in? Second. So we can almost imagine my velocity would be the feet per second over seconds. Or in other words, yeah, feet per second squared. Depending on how you want to write it, you can just write s squared or sec squared. The reason I'm using sec is because technically we use s for position, but then s for seconds is pretty standard also. So let's talk about what's happening at 1 second to this ball. So remember, I had my starting point, let's say where I'm standing, and we know, well, let's put it this way. After 1 second, my velocity is 10 feet per second. So which direction is my ball moving at 1 second? Is it moving in the positive direction to the right, or is it moving in a negative direction to the left? To the right. So yeah, that's the first thing we know, because it's a positive velocity. Positive velocity implies we're moving in the positive direction, whatever we decide that to be. We just said the right was a positive direction. And now I need to talk about the acceleration. So yeah, I'm moving to the right. What does this negative acceleration at 1 second mean? Yeah, that's one way how we can put it. How can we do this in more layman terms, common terms? Yes. In particular, if I want to even do it a little bit more general, this negative acceleration is telling me that not only is my ball moving to the right, but it is slowing down as I move to the right. Well, at least as at 1 second. So negative acceleration implies that I'm slowing down in that direction, at least. All right, so I've got the velocity and the acceleration at 1 second. Velocity tells me how is my position changing. Acceleration is telling me how is my speeding up or speeding down changing. It does tell us a little bit about the change in direction actually as well. And actually, based off this acceleration and velocity, without even having the function, I could have guessed that this ball was moving right and then eventually moving left. Because again, 1 second, positive velocity, I know I'm moving right. But since the acceleration is negative, it's slowly slowing down. And since the acceleration is still going to be negative for the entire time, it tells me I'm slowing down and eventually I'm moving in a negative direction. And in particular, if I kept on going, it would mean I would be speeding up in this direction as well. All right, so I have the velocity and acceleration. Any questions about what I did for this part B? Long story short, derivative for velocity, plug in 1. For acceleration, take the derivative, we plug in 1 again, if we need to. All right, so let's go ahead and move on to part C here. Let's see what I got. Determine the acceleration of the ball when its velocity is 0. So just so we have it again, we know that the velocity was 14 minus 4t. I'm just writing that again. And acceleration was -4. These were the functions I found in part A and B. So how do I even approach this problem? Give me the acceleration when the velocity is 0. There's 2 ways you can think about this. One way is a lot quicker than the other. Might be a slight trick question a bit. So I know I want to play around with the acceleration function. I know eventually I want to plug something into that acceleration function. So how would y'all approach this to even start us off? I claim that the solution here is clear. Yeah, look at that acceleration function. Is that acceleration ever changing? No, it's -4. There's not even a t in there. So yeah, I could figure out when the velocity is 0, but that's not going to matter. No matter what I plug into that acceleration function, it's -4. So this part doesn't even really matter for this particular example because the acceleration is the same no matter what. Your acceleration is not changing in this example. So really, the acceleration is still going to be -4 feet per second squared. In another example, if my acceleration had like a t in it, we would have to do some more work. If my acceleration had a t in it, I would first figure out when is velocity 0. That's going to give me some time. And then I would plug that number into my acceleration function. The only reason we didn't do it here is that it doesn't matter. Acceleration is the same no matter what in this example. All right, so this one was saying, the reason I was saying that it might be a slight trick question is that there's some people who look at this and say, all right, I need to figure out when velocity is 0, figure that all out, and then plug it in. But it doesn't matter. Acceleration stays constant in my example.
So instead of examples that are like this one, would it just also be easier just to look at it and tell what your velocity is and essentially what your acceleration is?
Yeah, so generally in these examples, I almost always recommend that you go ahead and, if you have position, go ahead and get your velocity and acceleration functions, because that's going to give you a lot of info. And it'll probably save you some grief later on, having to go back and forth.
And I think just looking at this one, you can tell that the acceleration is just -4 without having to do
Yeah.
that. Your velocity your initial is just 14, but then you don't think
Yes, correct. So yeah, you can always do it like how you were saying. Like I said, I always recommend that you go ahead and just go ahead and get that velocity and acceleration function, because it doesn't really take that much work, because we've just been doing a power rule, at least for what we're going to be dealing with. Any questions about this part C? As you can probably tell, most of our explanation went into part A and getting those foundations of our physics application. All right, so let's see. I think I have a part D. Oh, no, I don't. So let's talk about some takeaways from what we did in example 1. If I'm talking about one-dimensional motion, in the case we had left and right, when velocity is 0, that means my object is stationary. It's not moving. We know this because velocity describes how is my position changing. So it makes sense that if I'm not moving, my position is not changing at all. Hence, I have a velocity of 0. When the velocity is positive, this implies that we're moving in the positive direction, whichever way we decide that to be. In our examples, for convenience, we just said the positive direction was to the right. When velocity was negative, we went ahead and said that that I was moving in a negative direction, or in our example, moving left. But I'll still emphasize, there's a reason why I said positive direction and negative direction here, because our choice is actually arbitrary, because the location is relative to position. There was no real reason I said left was negative and right was positive direction, other than we're used to seeing negative numbers on the left and positive numbers on the right. But we could have easily swapped them around if we wanted to. So this just once again emphasizes velocity doesn't just give speed, it gives us direction of movement. And actually later on, and probably, I think it might be end of Cal 2 or beginning or somewhere in Cal 3, if you've done any physics, you might remember that there's a certain quantity that has magnitude and direction called a vector. If you haven't heard of vectors before, don't worry about it. But then those come up in, I believe, Cal 2 or Cal 3, depending on how it's scheduled. That can be directly related to what's being done here in later classes, especially whenever we're working with three-dimensional motion. I will also note that in all the examples we're doing for Cal 1, we're pretty much working in a vacuum. Pretty much we're not accounting for all these other scenarios. Like in a regular, very detailed physics problem, you might be accounting for some friction, air resistance, and stuff like that. But then we're just going to assume that we're working ideally here. Correct. All right, so these were my takeaways. Let's go ahead and look at my next example. So in example 1, we had one-dimensional movement going left and right. In other words, you can say almost horizontal, essentially. But I can also have one-dimensional motion going, for example, up, and down. So let's go ahead and talk about that. Here we go. Yes. So I want a cannon. So I get a cannon somehow. And what do you do with cannons? You shoot a cannonball out of the cannon. So let's say I want to go ahead and test a cannon, and I decide the best way to test this cannon is that I shoot a cannonball directly upwards. Is it the best idea? Maybe not, but for the sake of physics and calculus, we do it. And let's say somehow I know that this cannon, or whoever sold it to me, told me whenever I shoot a cannon, it shoots it out at a velocity of 15 meters per second. And furthermore, somehow I know that after 2 seconds, I know how far off the ground that cannon is, given by this function -0.3 t squared plus 15t meters. So for example, if I want to see how high the cannon is after 5 seconds, I'd plug in 5 in there, right? Because this is my position function. Or if I want to be a little bit more precise, I can say my height function. So going down this list, A is give me the velocity. B is when does a cannon hit its highest point? C is when it's at its highest point, how high is it? D is, well, when does it hit the ground? And E, with what velocity does it hit the ground? Let's assume that gravity is already accounted for in this function. Again, we're going to be working in a very ideal vacuum. We're not going to say, oh, what about air resistance? What about the weight of the cannonball? Let's say that's all accounted for in our function, for example. If we wanted to account for air resistance and all this other stuff, it would be a much more suffering problem, I'll put it. Which, I mean, we could do, but again, a little bit beyond the scope of what we're doing. So I'm going to go ahead and move this so I have the first question. So I still have the function here, and I have part A. Again, my function was my position height is given by S. And part A says, give me the velocity of the cannon after t seconds. So how do I get the velocity of the cannonball, v of t? How do I get velocity based off what I have already? Yeah, the derivative of position. So what's the derivative of that function? Let's see, here, fortunately, we just need a power rule, right? Bring down to 2, negative 0.3 times 2, we get negative 0.6 t plus derivative of 15t, we get 15. Great, we have the velocity function. Bless you. So again, anytime I'm asking for a velocity, I want the derivative of position. And one thing that you're going to find out pretty quickly in all these applications, if you really have no idea where to go from, usually a good general first step is take the derivative. That's going to be sort of a common theme here. And actually, let me go ahead and write this on the side so that I don't have to keep on remembering it each time. I said v of t was negative 0.6 t plus 15. And just so that we're all on the same page, what is going to be the unit velocity here? Yes, meters per second. Because velocity is the change in position over the change in time. Position is measured in meters. My time here is measured in seconds. So my velocity is going to be meters per second. Just a little side note for us as we go through this problem. But yeah, this is all we need for part A, taking the derivative. Any questions about pretty much doing the power rule here? All right, so I'm going to clear this. This is still on the board on the left, by the way. Mainly because this board doesn't let me do my animations and write at the same time. So let me see, does it turn to B or does it do my animation first? Oh, part B. So when does the cannonball reach its highest point? So we got to do some imagining of the scenario here to even figure out what's going on. So that's why I have this little animation with a cartoon cannon. Here I have a cannon and cannonballs. I take a cannonball and I stuff it into my cannon, and then I point it upwards, and then I shoot it up. It goes up in the air, and then eventually it has to go down. But before I let it go down, what has to happen for my velocity when it goes up and then it goes down? It does have to have a negative acceleration, but strictly talking about velocity, whenever it's going up, is my velocity positive or negative? Positive, right? What about whenever it starts going down? Negative. So to go from a positive velocity to a negative velocity, that means there has to be a point where my velocity is 0, because it goes from positive, 0, and then negative. So what can I say now about the velocity when it's at that highest point? Yeah, at that highest point, that velocity is actually going to hit 0. So it goes up in the air, and technically for a very brief moment, technically it is stopped with velocity 0, and then it goes down. Because we can't just go from positive to negative without hitting 0. So to figure out when my cannonball hits its highest point, I'm going to go ahead and say this is when velocity, which was this negative 0.6 t plus 15, was equal to 0. This is how we figure out part B. It reaches its highest point when velocity is 0. And then now we just got to figure out what is that time. And fortunately for us, our velocity happens to be a linear function or linear equation. So I need to get t alone, basically, solve for t, because I set it equal to 0 already. So I would subtract 15, and I get negative 0.6 t is equal to negative 15. And then I would divide by negative 0.6 on the left and the right. Sorry, I don't have enough room to divide it by this nicely. So I'm going to move here to the left. T is equal to negative 15 divided by negative 0.6. First off, that's a negative divided by a negative. We get a positive for sure, which is good. I'm not expecting negative time. 15 divided by 0.6. Someone go ahead and give that for me. 25. What's my unit of time? Seconds. In other words, what I'm saying here is that I take my cannon, I shoot it upwards, and it takes 25 seconds for it to reach its peak, after which it will begin to descend and hit the earth. And if you're doing this in a real world application, it is very unlikely that we had a perfectly vertical cannon and that the cannon would go back straight down into the cannon. Yes. All right, so we have part B. Notice here that this was not just something saying, figure out when v of t is 0. This is something that we had to decide from our scenario. Any questions about part B before I move on to part C and D? All right, so clearing this up, I still have the velocity function on the board off camera. That's my cannon going down and hitting the ground. So what is the height of the cannonball at its highest point? So how do I approach this problem? Yeah, we're going to take, because we know 25 seconds is when I'm at the highest point, and I want the height or the position. So really, I'm taking the height function and plugging in the time that we already found. So I can write this as s of 25. And actually, let me go ahead and see if I can pull up part D so I don't have to go through this part again. Oops, nope. Add it on a separate slide. So we, like I said, s of 25. So I'm going to plug 25 in there. If someone would be very so kind to plug that into a calculator for me. so I don't have to do 25 squared and 15 times head. Now I'll take your word for it, whatever pops up there. Yes, that is correct. What's the unit of measurement for the height? So in this case, my height, we're going to measure it in meters. Yeah, this is part of the thing where we have to be sort of careful about, am I working with position? Am I working with the velocity? Or if I'm working with acceleration? Each one has a different unit. So in other words, I'm working with this cannon. I shoot it up in the air. It takes 25 seconds to hit its highest point. And actually, it travels 187.5 meters in the air. So we're done with part C. We now know how high this cannon travels.
So is that the 0.3 supposed to be the acceleration?
It's not going to be negative 0.3, but we're going to see in a second the acceleration is actually going to be negative 0.6 because we do the derivative of this. All right, so I've got the scenario so far of that. So really, B and C were one sort of a paired question. For part B, you need to figure out how long does it take to get to the highest point. This one's asking, all right, what is the height when it hits the highest point? All right, so now we can do part D of this example. When does the cannonball strike the ground? Again, we're doing some ideas here. How does this relate to velocity and or my position when my cannonball hits the ground? I'm going to say the velocity that much. Also because I know in part E, I'm asking what is the velocity. So I know somehow I need to be working with my position function. What do I know about the position of my cannonball when it hits the ground? So when my cannonball hits the ground, y'all are along the right idea. My cannonball, let's say it just hits the ground, it doesn't pierce the ground. It's at height 0. So when it hits the ground, assuming that it doesn't go pierce the earth, my height is 0. I'm on the ground. So first I need to see when is my height or my position, S, which is this function. Actually, I can go ahead. Yeah, I'll write it again. S is equal to negative 0.3 t squared plus 15t. When is it equal to 0? So I'm calling on y'all's algebra skills to see how do I solve this equation. Yeah, we can take a t out because both of them have a t. Exactly what I wanted. Both of them have a t, so I can go ahead and factor out a singular t. And now I set each one equal to 0. This one, I get t is equal to 0. And then this one, I get negative 0.3 t plus 15 is equal to 0. And then I solve for t on the right. This one's a linear equation. I'm just going to do it very quickly. Also because I'm losing space down here. Oops, that's not supposed to be a plus, right? Equal there. Reset. I get negative 0.3 t is equal to negative 15. If I divide by negative 0.3, then I get t is equal to 15 divided by 0.3. I believe we get, 50 seconds to be exact. There's one thing I want to note here. I got two t values, t equal to 0 and t is equal to 50. Can anyone explain that for me? What does that mean for me to have two t values where my height is 0 based off my scenario? Why do I have two of them outside of calculation? Yeah, because whenever I start this whole scenario, I was already on the ground. At 0 seconds, my cannonball was on the ground. It went up and it went down after 50 seconds, back on the ground. A less dramatic version of this scenario would be if you just had, for example, a basketball that you threw up and then it came back down. Does anyone notice anything special about that 50, by the way? Yeah, it was just double the number it took to get to the highest point. And for this example, that was actually not a coincidence. This is actually related to, again, if you might have done this in some physics class where you did like trajectory, stuff like that. Your highest point and then hitting back the ground, it actually takes half the time. So we have 50 seconds is when I hit the ground. And now we can finally do the last part of this question before we move on. This is just my picture again. With what velocity do I hit the ground? So enlighten me and tell me, how do I even tackle this last question before we move on to the next one? 50 into what? Into which function? Because we have two functions. Do we plug it into S or do we plug it into V? Well, what am I looking for? Yeah, I'm looking for a velocity. So I should plug it into V. So again, we know it hits the ground at 50 seconds, and I have my velocity function. So I'm just going to plug in 50 for t. So I get negative 0.6 times 50 plus 15. So negative 0.6 times 50, what do we get from that? What, negative 30? And then negative 30 plus 15, I believe we get negative 15 meters per second. Again, we're expecting it to be a negative velocity because it's going down. So this also leaves a question, would you want to be around that area when this cannonball goes down? Definitely not. Well, first off, big reason is that you don't want to get hit by a cannonball, even if it was moving really slow. And the other reason that this will likely kill you because it's moving at 15 meters per second. If the cannonball didn't knock you out, whatever happens after will.
Did you even calculate the size of the cannonball or the mass?
Hopefully, for y'all's sake, it's like a foam cannonball, but that's still pretty fast-ish. I think so. That is true. And also, we're assuming that my functions here are already accounted for: air resistance, all gravity, all those special buzz physics words. All right, so that finishes example 2, and I'm just going to show you example 3. Obviously, we don't have enough time to do it today. I just want you to look at example 3 for a moment and then think about how do we approach it. So I want more people to have access to math. So the best idea is that you throw math textbooks from the top of the building. They are still getting their math knowledge somehow, one way or another. So my great plan is to go to the top of this building and throw, obviously, textbooks at people. And let's say that this tower is 784 feet tall, and The position is actually denoted by, found by this function, 784 minus 16t squared feet. We're going to talk about how do I get the velocity, how do I get the acceleration, and for my little animation, here's my textbook. And what happens whenever you throw a textbook at people from the top of a building? And then you run off. All right, so that's what we're going to do next time. Unfortunately, we won't talk about how you run away from that. But this is example 3, and actually the last one for this section. More than likely, I think on Monday, we'll be strictly finishing this example. And then on Tuesday, we'll talk about the secondary application related rates, very applicable for those of y'all in engineering, which I think happens to be everyone in here at the moment. All right, besides that, that's all for today. I'll see y'all on Monday. Have a good weekend.